Hello everyone, I welcome you all for the 9th session of the chapter Ray Optics. In this session, we will be solving some of the problems regarding the chapter Ray Optics. Let us solve it one by one. The first problem is, I will read out the problem. Two convex lenses of focal lengths 0.20 meter and 0.30 meter are kept in contact. Find the focal length of the combination. Calculate the powers of the two lenses and the combination. First, let us write the given things, given data. So there are two lenses of focal length 0.20 meter and 0.30 meter. So these two lenses are kept in contact. The two lenses are kept in contact like this and they are placed coaxially. So we need to find what is the effective focal length of the combination and also powers of the two lenses and also its combination. So first let me find what is the effective focal length of the combination of the lenses. Effective focal length. So we have a formula for finding the effective focal length. This is 1 by f is equal to 1 by f1 plus 1 by f2. So 1 by f is equal to f1 is 0.20 meter. So this is 0.20 meter plus f2 is 0.30. This is 0.30. Let me take LCM for this. This is 1 by f is equal to, this is 0.20 into 0.30 and in the numerator 0.30 plus 0.20. So this is 1 by f is equal to, this will be 0.5 divided by, this will be 0.06, and if I want f, what I can do is I can reciprocate this. So 0.06 divided by 0.50. So what does it gives is 0.12 meter. So we got the value of effective focal length of the combination of lens as f is equal to 0.12 meter. Okay? Yes. Then they have asked one more question here. What is the power of the two lenses and also its combination? So let us find that. Secondly, power of the two lenses. So first, for the first lens, power is equal to 1 divided by its focal length. So 1 divided by focal length of the first lens is 0.20, so that the power will be 5 diopter. Okay, diopter is a unit of power of a lens. Next, for the second lens, power is equal to 1 by f2. So this is 1 by 0.30 and this will give us 3.33 recurrence. So this is 3.33 diopter. So power of individual lenses, P1 is equal to 5 diopter and P2 is equal to 3.33 diopter. Now we need to find the effective power of the combination of the lenses. So how do you find this? Let me write it here. So this is power of the combination of lenses. So power is equal to P1 plus P2. It is simply adding the powers of each lenses. So this is equal to 5 plus this is equal to 3.33, and if I add these two, what you will get is 8.33 diopter. So the power of the combination of the lenses is 8.33 diopter. Well, we will move on to the next question now. Now the second problem, an equilateral prism produces a minimum deviation of 40 degree. What is the refractive index of the material of the prism, and also calculate the angle of incidence. Let's do this. So let us write the given things. They have given that for an equilateral prism. So if it is an equilateral prism, the angle of the prism is equal to 60 degree. Okay, for an equilateral prism, angle of the prism is 60 degrees. Next, the minimum deviation produced by the prism is equal to 40 degree, and what we need to find is what is the refractive index of the prism, and also we need to find out the angle of incidence. So let us do this. We know that we have a formula for relating the refractive index, angle of the prism and angle of minimum deviation. So what is that equation? N is equal to sine of A plus D by 2 whole divided by sine of A by 2. So this is the formula for finding the refractive index of the prism. Let us substitute the things. N is equal to sine of A plus D by 2. Angle of the prism is 60 degrees. This is 60 plus angle of minimum deviation is 40 divided by 2 whole divided by sine of A by 2, that is 60 by 2. So let's continue it further. N is equal to sine of 60 plus 40 by 2. 60 plus 40 is 100. 100 by 2 is 50. So sine of 50 degree divided by sine of 60 by 2 is 30. So this is sine 30 degree. Now let us do this sine 50 degree. So you can look at your Clark's table or logarithmic table. You can find the value of sine 50 degree. So in the natural science page, under the first column you have 50 degree. So you need to look at 50 degree 0 minute. So what is the value of sine 50 degree? So the value is found out to be 0.7660 whole divided by sine 30. Sine 30 is 1 by 2, which is equal to 0.5. So now if I divide these two, what I will get is 1.532, correct? So if I round it off to the second decimal place, which is a standard representation, so n is equal to 1.53. So this is the refractive index of the material of the prism. A refractive index is a unitless quantity, so n is equal to 1.53. It is not having a unit or dimension. Now we have to find the angle of incidence also. So in the second case, angle of incidence. To find the angle of incidence, so what is the formula for finding the angle of incidence? I is equal to A plus D by 2. This is the formula for finding the angle of incidence. So angle of the prism is 60 degree and angle of deviation is 40 divided by 2. So 60 plus 40 by 2 is 50. So the angle of incidence is equal to 50 degrees. So we have find refractive index of the material of the prism and also its angle of incidence. We'll move on to the next problem now. Now the third problem. An equilateral prism made of glass, when a parallel beam of light is incident on one face of a prism, the angle of minimum deviation is found to be 40 degree. Calculate the refractive index of the prism. If this prism is placed in water of refractive index 1.33, find the new angle of minimum deviation for the parallel beam of light. So let us write the given data first. So they have given that we have an equilateral prism. So for an equilateral prism, angle of the prism is equal to 60 degrees. You know that. And the deviation produced, the angle of minimum deviation produced by a prism is equal to 40 degree again. And we need to find the refractive index of the prism. So we have already find this in the previous problem itself. So first, for finding the refractive index of the prism, we'll be using the same formula. N is equal to sine of A plus D by 2 whole divided by sine of A by 2. And let us substitute the things. Sine of A plus D by 2 is 60 plus 40 by 2 whole divided by sine of A by 2 is sine of 60 by 2. Now N is equal to sine of 60 plus 40 by 2 is sine 50 degree divided by sine of 60 by 2 is 30 degree. So sine 50 degree is 0.7660 divided by sine 30 is 0.5. So you will get 1.53. So we got the value of refractive index of the prism. So this has already been done in the previous problem. Now in the second case, what we are doing is we are immersing the prism inside a water of refractive index 1.33. So the prism, an equilateral prism, is now being placed in a water medium. Okay, this is in a water medium. So when the prism is immersed in a water medium, what happens is the refractive index of the material of the prism is now written in terms of refractive index of the water, that is a relative refractive index. So initially when the prism is in air, in this case the prism is in air. So for air the refractive index is equal to 1. So we are just writing the absolute refractive index. But in this case, when the prism is immersed in a water, what happens is the refractive index of the material of the prism changes. And for this case, now we need to find the angle of minimum deviation. So the prism is immersed in a water now. So in the water, the refractive index is written as N21, which is equal to N2 by N1, correct? N2 is the refractive index of the prism. N1 is the refractive index of the water medium. Previously it is in air, that is why N1 is equal to 1 in that case. So in this case you need to consider N1 is the refractive index of the water. So let us write this. The refractive index of the material of the prism is now written as N21, and we have a same formula, sine of A plus D dash by 2. Okay, angle of the prism will not changes, it will be 60 degree always because it is a equilateral prism. And when it is immersed in a water, for a same angle of incidence, the deviation will change. So we need to find what is this D dashes. So this divided by sine of A by 2, correct? N21 is equal to N2 by N1, correct? So let us substitute this. So N21 is equal to N2 by N1. Let me write this as N2 by N1 is equal to sine of A. Angle of the prism is same, which is equal to 60 degrees. So this is 60 plus D dash. D dash is the angle of minimum deviation produced when the prism is in water medium. So this divided by 2, whole divided by, and this is sine of A by 2. A by 2 is 60 by 2. So let us substitute the value of N2 and N1. So N2 is nothing but a refractive index of the material of the prism with respect to air. So this N2 is written as 1.53, which is already found, correct? Divided by N1. N1 is the refractive index of water, which is given as N1 is equal to 1.33. So let me write this as 1.33. This is equal to sine of 60 plus D dash by 2 whole divided by sine 60 by 2 is sine 30, correct? This is sine 30. Let us rearrange the terms. I will take this in left hand side. So sine of 60 plus D dash by 2 is equal to 1.533 into sine 30 goes to here. So sine 30, I will write it directly as 0.5. Sine 30 goes to here. Sine 30 is 0.5 divided by 1.33. So sine of 60 plus D by 2 is equal to, if I do this calculation, what you will get is 0.5752. Okay. So 60 plus D by 2 is equal to sine inverse of 0.5752, and this is 60 plus D by 2 is equal to, if I find this angle, what you will get is 35 degree 7 minutes. Okay. Now 60 by 2 is 30 degree plus this is D by 2, which is equal to 35 degree 7 minutes. Now take this 30 degree to the right hand side, and what you will get is D by 2 is equal to 35 degree 7 minutes minus 30 degree. So D by 2 is equal to 35 degree 7 minutes minus 30 degree. So this can be written as 0 minutes also. So 35 minus 30 is 5 degree, 7 minute minus 0 minute is 7 minute. So D by 2 is equal to 5 degree 7 minute, or D is equal to, this is D dash. So D dash is equal to, multiply 2 here, so this becomes 10 degree 14 minutes. So the deviation produced when the prism is immersed in a water will become 10 degree 14 minutes. Okay. Now we'll move on to the next problem. Let's read out the fourth problem. The radii of curvature of two surfaces of a convex lens is 0.2 meter and 0.22 meter. Find the focal length of the lens if refractive index of the material of the lens is 1.5. Also find the change in focal length if it is immersed in water of refractive index 1.33. Well, in this problem, they have given that we have a convex lens of two spherical surfaces, out of which the first spherical surface is having a radius of curvature of 0.20 meter and the second surface is having a radius of curvature of 0.30 meter. Okay. Now, what we need to find is what is the focal length of this lens if the refractive index of the lens is given as 1.5. In the first case, the lens is placed in air. Okay, this is air and this is nothing but a glass medium. They have given the value of refractive index of this glass as 1.5. So here the refractive index is written in terms of air. That is nothing but an absolute refractive index. So here the radius of curvature of the first surface and the second surfaces are given, but we should consider this is negative because the radius of curvature for the second surface is in the left hand side of the optical center, correct? So the distances measured to the left of the optical center are taken as negative. So R2 is equal to minus of 0.30 meter. Well, initially the lens is placed in air, therefore the refractive index of the material of the lens is considered with respect to air. Okay. So the focal length in the case 1, the focal length of the lens. Now we'll be using a lens maker's formula. So lens maker's formula is 1 by f is equal to n21 minus 1 into 1 by r1 minus 1 by r2. This is the lens maker's formula, correct? We have derived this. So in this case, since the lens is placed in air, n2 is equal to 1.5 and n1 is equal to 1. Refractive index of air is 1. So now this n21 is written as n2 by n1 minus 1 into 1 by r1 minus 1 by r2. Now let us substitute the things. This is 1 by f is equal to n2 by n1. n2 is 1.5 by n1 is 1 minus of 1 into 1 by r1 is 0.20. This is 0.20. Oh sorry, this is not 0.30. It is 0.22 actually. Okay, this is 0.22. So R2 is minus 0.22, therefore this is minus of 0.22. So this minus will multiply with this, so minus into minus becomes plus. Now 1 by f is equal to 1.5 by 1 is 1.5, 1.5 minus 1 into 1 by 0.20 plus 1 by 0.22. Now if I do this calculation, this is 0.5 into 0.20 into 0.22 in the numerator, 0.22 plus 0.20. So if I find this value, what I will get is 1 by f is equal to 4.7727. And if I want f, I can reciprocate this. So 1 by 4.7727 and this will be equal to 0.21 meter. So we got the value of focal length when the lens is placed in air. Now what we are doing is the lens is completely immersed in water of refractive index 1.33. Now what happens is n2 is equal to 1.5 but n1 is not equal to 1 now, it is equal to 1.33 as the lens is placed in water. So what happens to the equation now? Using the same expression, the focal length of the lens changes inside the water, so we are writing 1 by f dash. So 1 by f dash is equal to n21 minus 1 into 1 by r1 minus 1 by r2. These values will not change. Let us write them as it is. 1 by f dash is equal to n21 now becomes n2 by n1 minus 1 into 1 by r1 minus 1 by r2. Now 1 by f dash is equal to n2 by n1 is 1.5 divided by 1.33. So this is minus 1 into 1 by R1 is 0.20 minus of, this is, I will write it as plus only. You know why I am writing this as plus. So this is 0.22. So if I find the value of this, what you will get is, so this becomes 0.1278 into this will be 9.5454. So if you do this calculations, you will get 1 by f dash as 1.2199. And if I want f dash, so we want f dash there, so I will write it here. So f dash is equal to reciprocal of that 1 by 1.2199. So this will be 0.82 meter. So we find the value of focal length when it is immersed in water. They have asked for calculating the change in focal length. So for the change in focal length, so change in focal length is delta f, that is equal to f dash minus f. F dash is 0.82 minus f is 0.21. So this will be 0.61 meter. So there is a change in focal length of 0.61 meter when the lens is immersed in a water of refractive index 1.33. Fine. We will move on to the next problem now. An object of height 3 centimeter is placed 14 centimeter in front of concave lens of focal length 21 centimeter. Find the position, nature and size of the image formed. First, let us write the given data. So they have given that height of the object. So the object height is given as 3 centimeter and which is placed 14 centimeter in front of a concave lens. That is nothing but a object distance. See, this is a concave lens. This is a concave lens. This is the principal axis and this is optical center. So the height of the object is given, HO is equal to 3 centimeter and this is placed 14 centimeter in front of a concave lens. So this distance is equal to 14 centimeter. Since this distance is towards the left side of the optical center, the object distance is considered as negative. So minus of 14 centimeter. And they have given the value of focal length of this concave lens. The focal length of the concave lens is given as 21 centimeter, but for a concave lens, the image is always going to form on the same side as the object, that is towards the left side. So that this distance is also considered as minus. In the sign convention itself, we have mentioned that the focal length for a concave lens is negative. So we need to find the position, nature and height of the image. Now to find the position of the image, firstly let us find the position of the image. To find the position of the image, we will be using a thin lens formula. So what is a thin lens formula? 1 by f is equal to 1 by v minus 1 by u, where f is the focal length, v is the image distance, u is the object distance. So we need this v, that is the image distance. So let us substitute for v. 1 by v will be equal to, this comes to here, so 1 by f plus 1 by u. This is 1 by v is equal to 1 by f, f is minus 21 plus 1 by u, u is minus 14. So here you can take minus of 1 by 7 common, correct? Minus of 1 by 7 is taken outside. So what remains here is 1 by 3 plus here 1 by 2, correct? So the next step is 1 by v is equal to minus 1 by 7 is kept as it is and take LCM here. So 3 into 2 is 6, 2 plus 3 becomes 5 and this will be 5 by 6, correct? So 1 by v is equal to minus 5 divided by 42. But if I want v, we get minus 42 by 5 minus of 8.4 centimeter. So that we got the value of image distance. That is, the image is placed at a distance of minus 8.4. That is towards the same side as the object. So the image distance v will be equal to minus of 8.4 centimeter. Now we need to look at the nature and size of the image. For that we need to find the magnification. Okay, how do you find the magnification? Secondly, to find the nature and size of the image. Let's find the magnification M. So magnification is equal to M. So the magnification formula is Hi divided by Ho, correct? To find the magnification we have a formula Hi by Ho. Let us do this. M is equal to Hi by Ho. But magnification for a lens is also given by V by U. So V by U is equal to Hi by Ho. If I want this high, Hi is equal to V by U into Ho. So V is equal to minus 8.4 divided by U is minus 14 into height of the height of the object is 3, which is in the upper side, therefore it is positive. So height of the image will be, this minus and minus gets cancelled, it is 1.8 centimeter. So it is positive, means the image is erect image. The height of the image is found to be 1.8 centimeter. Now, to understand the nature of the image, we need to find its magnification. So magnification is Hi by Ho. This is 1.8 divided by 3. This is 1.8 divided by 3 and this will be 0.6. So the magnification is 0.6, means it is less than 1. Then the image will be diminished image. And magnification is positive, means the image is a virtual image. Therefore, what is the nature of the image now? The image is a diminished image and also a virtual and erect image. Let us write that. The nature of the image is diminished and virtual and erect. Virtual and erect. So this is the nature. The position of the image is 8.4 centimeter in the negative side, that towards the object side, and the height of the image or the size of the image is 1.8 centimeter. This is 1.8 centimeter, and the nature of the images, as the magnification is plus 0.6, since it is positive, it is a virtual image. As magnification is plus 0.6, the image is a diminished, virtual and erect image. Okay.